Alright, boys and girls, this is your chapter 6.1 notes, higher degree polynomial functions. And so what we mean by higher degree is basically just higher than 2. Alright, we've talked about lines, we've talked about quadratics, which are basically just degree 2 polynomials. So anything higher than that we call them higher degree polynomials. We have special names for two of them, the cubic and the quartic. That's degree 3 and degree 4 respectively. And again, it just means degree 3. Degree just means the highest exponent is a 3, alright, and degree 4 means the highest exponent is a 4. So when I say a degree 2 was a quadratic, that was just it had an x squared in it as the highest power. And then anything above degree 4, we just call it a degree 5 polynomial or a degree 6 polynomial, degree 11 polynomial, whatever. Usually we don't see many things higher than 4. That's why we don't really give them names. I mean, technically we call it a quintic if it was degree 5, but really we only give special names up to 4. Just because of familiarity, that's what we mainly see. This next slide tells us a little bit about polynomials and their graphs. So if you have a polynomial degree n, we have at most n minus 1 turning points. So that means if it's degree 4, 4 minus 1 is 3, so at most 3 turning points. Right? Degree 2, a parabola, has 2 minus 1, 1 turning point. So that's the vertex that we're familiar with. So that's what that top line there is saying. The second one, the graph of polynomial function degree n has at most n x-intercepts, so it could cross the x-axis at most whatever the degree is. So if it's degree 5, you can cross at most 5 times. If it's degree 2, again a parabola will only cross at most 2 times. Alright, and then you have a degree 25 polynomial could cross up to 5 times that x-axis. And then end behavior, that's something that you see a lot when you're dealing with polynomials. End behavior is just how the polynomial behaves at the end of the graph, the left side of the graph, the right side of the graph. We're not concerned with it bending and twisting and doing all that stuff in the middle, just what's going on the left end and the right end. That's what we call end behavior. They use for this textbook opens up on one end, opens down on the other, opens up on both ends, whatever. I'm used to saying rises to the left, falls to the right, rises to the right, falls to the left, that kind of thing. But they use this opening up, opening down, which is fine. Alright, so odd degree, it changes what it does on one end to the other. So odd degree, notice one end opens up, one end opens down. So here's an example down here. 5 is an odd degree. Oops. Alright, so we have an odd degree example here, and what does it say odd will do? It says it'll open up on one end, so here's the end that goes up. Alright, and then it goes down on the other. Here's the end that it goes down. Alright, and then even degree, it does the same thing on both ends. Opens up on both ends or opens down on both ends. So here's an even degree. And again, degree just means that highest exponent. So the highest exponent in this thing was 6. The highest exponent up here was 5. So that's why this is even degree. Alright, and again, even degree, it agrees what it's going to do on both ends. It opens up on this end. It also opens up on this end. Okay, so this one, it opens down to the left, it opens up to the right. This one opens up on both ends. Or again, what I normally teach people, this falls left and it rises right. Right, that's the end behavior of this polynomial. Alright, and this one just rises both left and right. And again, this is what I'm talking about with end behavior. We don't care about what happens in the middle. Yeah, this thing bends and it slowly crosses the x-axis and then it turns back up. This one bends, slowly touches the x-axis, and turns back down and then turns back up. We're not concerned with all that stuff. It's just what happens at the end. What happens on the right side, it goes up. What happens on the left side, it goes down. What happens on the left side, it goes up. What happens on the right side, it goes up. Okay, so when we talk about end behavior, we strictly mean the far ends, left and right. Alright, and then this is again something that you may want to pause and write all this stuff down, because this is important for end behavior and just in general with polynomials. So what this is basically is telling you is the behavior of polynomials. So linear, a line is a polynomial. Okay, it's just a degree 1 polynomial. Alright, so a line is a degree 1 polynomial. Okay, positive sloping line and negative sloping line. Alright, if you have a positive leading coefficient, that means you have a positive slope. So your end behavior is it rises to the right, it falls to the left. Right, if you have a positive slope. If you have a negative slope, you have a negative leading coefficient. Right, and that means you rise to the left and you fall to the right. Right, so lines are odd degree. Right, lines are degree 1. Right, and then quadratics, we've talked about them before. Right, parabolas, a positive leading coefficient means it opens upward, a negative leading coefficient means it opens downward. And again, leading coefficient determines the end behavior. So a leading coefficient being positive, it's going to do this. Right, leading coefficient of negative, it's going to do this. So this one's even degree, degree 2. And again, even degrees agree on both ends, up and up or down and down on the ends. Alright, and now make your way to the two new ones we talked about, cubics or quartics. Now the thing about these that's different than lines is we don't exactly know what's going to happen inside the end behavior. See, this has a subtle little it doesn't turn drastically like this one does. It just has a slow turn and then it turns right back up. Alright, but cubics, if they have positive leading coefficients, again we can have just a single, not really a change of direction, just like a slow turn and then it turns back the other way, or we can have like a U-turn almost, and then it turns back again, a second U-turn. Right, and then if it's a negative leading coefficient, notice it's going to go back down the other way. So this again, if you go back up to the top of this page, this is positive leading coefficient for a cubic. So if you have a positive leading coefficient, it starts off negative and it makes its way positive, or you could say it falls left, rises right, just like it was with the line. Alright, line, positive leading coefficient, fell left, rose right. Same thing with a cubic. Alright, and then if it's a negative leading coefficient, same again with the line. It rises left, it falls right, just like the line did. Alright, cubic, that's odd degree, but specifically it's degree 3. Alright, then quartics again. Quartics, in between the arrows, in between the ends, it can have it looks like just a single slow turn back up. It can have a couple of subtle turns, so there's a 1, a second, and a third subtle turn, or it can have 3 very drastic turns. Right, all of these are quartics. And then if it's a negative leading coefficient, again just flip it over and it opens downward instead of opening upward on the ends. Alright, so this behaves exactly like the quadratic does in the end because it's even degree. Alright, remember the degree determines the end behavior. Alright, so again I would pause that and write all that down. In the middle here, number of turning points. Linear doesn't turn at all. Remember, it's a line, so it doesn't turn. A quadratic, the vertex is with the one turning point. Now, this says number of turning points is 2 or 0 for a cubic. Okay, and what they mean by that is this turns and changes direction, then turns and changes direction. So that's 2. But they're saying here that this doesn't change direction, so it's not necessarily a turning point, but it does. It does. I guess we could call it a curve. All right, it's not straight. All right, so it doesn't mean if it has no turning points, it's going to look like a line. This is what it means by it has no turning points. It doesn't completely change direction and turn back the other way. All right, so I just wanted to make you be aware of that. All right, and then a quartic. Again, they're saying 3 or 1. So this is what I was talking about, 3 subtle little turns. All right, or 3 drastic turns, or 1. It's just saying 1 complete turn. All right, that's if you have just something like x to the 4th. It's just going to look like a slow, kind of flattened out quadratic. All right. So be aware of that, especially with the cubic. 0 turns does not mean it's going to be a line. It's just no drastic U-turns. Alright, and then here's some examples, some problems you might see in your homework. So these 4 figures, they want us to do these things to them. Give the number of x-intercepts, the number of turning points, leading coefficient is positive or negative, where the degree is even or odd, and the minimum possible degree. So let's go through these and see what we can come up with. And let me move this down a little bit so I have some room to actually do this. Alright, so for this one they want to start us off with the number of x-intercepts. So obviously right here is an x-intercept, and then here's another one. Alright, so for part 1 we have 2 x-intercepts. Alright, over here for this one we've got 1. We got 1 right here, and then 1 right here. Alright, so 1 for this one, we have 3 x-intercepts. Alright, the number of turning points. This one has a single turning point, so 1 turning point. Alright, then if you look back at the other one, it had 1, 2, 3 turning points. Alright, part 3. Whether the leading coefficient is positive or negative. Alright, this one is even degree. Alright, which will kind of jump ahead to 4. Let me jump ahead to 4 because that's easier to understand why I know what the leading coefficient is. This is even degree, as is this one. Alright, the reason is, again, because the end behavior agrees on both ends, up and up, down and down. And when the end behavior agrees, that means you have even degree. Okay. And now jump back to 3, where the leading coefficient is positive or negative. Alright, when you have even degree, if it's up and up, then you have a positive leading coefficient. Alright, if it's down and down, then you have a negative leading coefficient. Alright, so this is positive because the end behavior was up and up. This is negative because the end behavior was down and down. Alright, now the last part. What's the minimum possible degree? The minimum possible degree on both of these is degree 4. Now you may say, well, how could this one, the minimum degree, be 4 if it has just a single turning point? Couldn't it possibly be degree 2? And my answer to that is, well, technically yes, it could be, but I'm looking at it right here. It flattens off almost completely, and a parabola will not do that. A pure parabola, meaning a quadratic, will not do that. When it gets to that vertex, it turns. It won't flatten off like this. Okay, so because of that, I say degree 4. Alright, and then this one over here, because it has 3 turns, it has to be degree 4. Okay, so that's why it has the 3 turns, is why I'm saying it's degree 4. Alright, but this one, I'm saying it's degree 4 because it's too flat when it turns to be degree 2. Alright, now these, the same thing. Step 1 was come up with their x-intercepts. Alright, so this one has one right there, about a half. So we just have one x-intercept, and it was 1/2, 0. Alright, over here we have one at -2, we have one at the origin, we have one at +2, so we have 3 x-intercepts. Alright, part 2 was how many turning points. So this one looks like it has 0 turning points. Alright, this one looks like it has 1, 2 very obvious turning points. Now again, I'm going to skip 3 and jump to 4 because it's easier to do the even and odd versus positive negative. So this one, on both of them, again, we have opposite end behaviors, meaning on the left end it's doing different than what it's doing on the right end. So left end we're rising, then falling. On this one, left end we're falling, right end we're rising. So because we're doing opposites, this is odd degree. Alright, and then for odd degree, if it falls to the left, rises to the right, then it's positive leading coefficient. If it rises to the left and falls to the right, then it's negative. So for this one, we're rising left and we're falling right, so that's a negative leading coefficient. Alright, rises left, falls right, that's negative. And then this one's positive because it does just the opposite of that. It falls left and rises right. Alright, if you have trouble remembering this, just throw an odd degree function into your calculator, like y equals x cubed, and graph it. Okay, oops, let me hit zoom 6. Zoom 6 gets me back to the standard window. So this is y equals x cubed, okay, odd degree, alright, and it falls left, it rises right. Okay, if I stick in insert a negative and graph it, now it rises to the left and falls to the right. Okay, so if you can't remember, just throw it in your calculator to help you remember. Alright, here's a applied problem question. So using data from 2000 and projected to 2015, this function, this quartic here, can be used to model the U.S. unemployment rate with x equal to number of years after 2000. So we want to graph the function from 0 to 15, alright, from 2000 to 2015, alright, and then we're going to do these other two parts. So here's part A. Again, I've already got the graph. I've used the book that I got the questions from to give me the graph to not have to actually do it by hand. But anyway, this is what that thing would look like if you graphed it. Alright, in this window from 0 to 15. Alright, this little dash here means we've cut the graph, so it starts at 4, 5, 6 and it continues. So from 0 to 15, from 4 to 11, you get this, something looks like this quartic. Now remember, a quartic can turn 3 times, so there's 1, there's 2, it bends back the other way, and then there's the third one. Okay? So there's what the first part looks like. Now part B, use the graph and technology to approximate the year after 2000 which the unemployment rate maxes out. Alright, so I put it in my Y1 in my calculator. Okay, so here's that function. Alright, all the way through in my calculator. And then again I made the window from 0 to 15. Alright, and then I did from 3 to 11 just because this starts at 4, so there's a little gap there. So just to make it look like this, I did 3 to 11. Alright, and I graph it, and there's that same shape that we see here. Okay, and it wants to know where it maxes out. So this is where we use our second calc. Alright, and we come to the maximum, number 4. Alright, so left bound, remember that means try to get to the left side of the peak. So somewhere around here. Right bound, get to the right side of the peak. So we've moved past the peak to the right. And then for guess, you can just hit enter, but get as close to the peak as you want and then hit enter. It does its little thing, and then there's our maximum. Now I went ahead and put that in here. This is our maximum. X is what we're after. Okay, because again, if you look at the way the question's worded, it says approximate the year after 2000. So X is equal to the number of years after 2000. Alright, so 12 and some change years after 2000. Now 12 years after 2000 is 2012, and if we're assuming that we're talking about X equals 0 means the end of 2000, then something like 0.1 would be in 2001. Alright, so 12 is the end of 2012, so 12 and some change, this would be sometime in the year 2013. So sometime in 2013, unemployment reaches a max of 9.49 roughly percent. Alright, but it also wants us to, if you read the question, it also wants us to find a period after 2002 before 2015 which it's a minimum. So we can't just say, alright, in 2000 it was at its lowest point. We have to go after 2002. So it reaches a minimum after 2002 as well. So go back to your calculator. This time go in there into the calc menu, second trace, and highlight minimum. Alright, so after 2002, okay, so we can make our left bound 2. Okay, that means after 2002. And then right bound, it kind of goes down below right here. So that's our, looks like our minimum after it kind of goes up and then it comes back down. So after it starts to go back up again, hit enter and then go back to that guess. Alright, it does its thing, and then there's our guess. Alright, then the same thinking as before. If 0 is the end of 2000, then 3 is the end of 2003, so this is sometime in 2004, nearly the end of 2004. So sometime in 2004, unemployment reaches a minimum of 5.25%, roughly, to 2 decimal places. Alright, and then don't forget part C. Is it likely that this model can be used to estimate the U.S. unemployment rate for long after 2015? Okay, think about this. This is degree 4 polynomial. So it can only have 1, 2, 3 bends. There they all are. So it can't bend anymore. So what's going to happen? This thing is just going to keep on keeping on. It's going to just go down and down and down and down and down and down forever and ever and ever. Okay, now think about that. It is truncated. I mean, it is cut. So this isn't 4 then 0. So it is going to go down through 3 and 2 and 1. But still, what happens after it goes to 0? Down here, this is negative. Right? Does it make sense that the unemployment rate could be negative 4.3%? Okay, no, that doesn't make any sense. So our answer to part C is a resounding no. Alright, so the not graph, but the model. The model is useless, not uses, useless once y is negative. Alright, and then this last page, this is just some examples from questions from your homework. So I'll do that on another video.